Hello everybody, welcome to the 6th week of our course. Now remember, this is on Chapter 6, the normal distribution. We'll talk about the standard normal distribution and calculations using normal probability. My task here is to talk a little bit about the normal distribution, but mostly to introduce some of the ideas that we'll be able to use using Microsoft Excel to help us make these calculations. A couple of reminders is that by Monday of the 6th week, don't forget that you need to post to Discussion Board 3 and complete the Chapter 5 web-assigned homework. By Friday of the 5th week, don't forget you need to watch the Chapter 6 lecture, this lecture, along with the publisher videos, along with the Lecture 6 form for attendance. So the focus on this chapter is on continuous random variables and specifically normal distributions. Now, what we've said so far, we discussed this in Chapter 5 when we talked about continuous random variables and the uniform distribution, among others. We said that the normal distribution was a continuous random variable as well, but the curve is bell-shaped and symmetric, and there's a function here that would describe the probability density function, f of x, as e to the negative 1/2 x minus the mean squared mean over the standard deviation squared, all divided by the standard deviation times the square root of 2 pi. Now, how pi snuck its way into this formula is an interesting story, but one we're not going to explore. The distribution is determined by fixed values of the mean and standard deviation, however, which is more of the point that we need to know in order to be able to operate in what we're doing this week. Let's remind ourselves what is meant by a density curve, which is a graph of a continuous probability distribution. It must satisfy the following properties. The total area under the curve must equal 1. And that every point on the curve must have a vertical height that is 0 or greater. That is, the curve cannot fall below the x-axis. Being that this is the case, we can say that the total area under our density curve, the normal curve, is equal to 1, and there is a correspondence then between the area and the probability. In the normal distribution, the mean is where most of the density is going to fall. So this is going to be the highest concentration or the highest relative frequency associated with that, and we could draw a vertical line representing that height right here at the mean. Say this area, this represents exactly half of the area. Half of the area would be to the left of the mean, half the area to the right of the mean. We also could use our empirical rule to talk about what happens between -1 standard deviations and +1 standard deviations within the mean, and 2 standard deviations to the left and 2 standard deviations to the right of the mean, and so on. But some facts about this curve are in order right here. So let's talk about one or two of these things. The normal distribution is a continuous probability distribution, as opposed to a discrete probability distribution like the binomial or Poisson distribution curves that we've talked about in the past. It's sometimes called a bell curve. It represents a family of curves that shape depends on the standard deviation, so we can have the same mean, but the standard deviation changes the shape of that standard normal distribution graph. So we want to make sure that we understand when we say the normal curve, we're talking about a family of curves based on the standard deviation. Now, by the law of large numbers, which we will discuss in week 7, the law of large numbers indicates that in any sample of continuous variables with a large enough size, the distribution will approximate the normal curve, which is a very interesting effect and one that we'll explore in more depth next week. But the total area under the normal curve is equal to 1, and I've made an illustration here that shows you that if we take half of the area to the right of the mean and half of the area to the left of the mean, we get the whole area equal to 1.0. Again, a very important fact for us to keep in mind. So we're going to start our first part of our chapter by presenting what's called the standard normal distribution, which has 3 properties. First of all, like all normal distributions, its graph is bell-shaped. What's special about this curve is that the mean is equal to 0 and the standard deviation is equal to 1. And we want to develop the skill to find areas, which we sometimes might call probabilities or relative frequencies, corresponding to various regions under the graph of the standard normal curve. We can find z-scores that correspond to those areas under the curve, and that's a very useful task for us to have and will affect the way that we handle the rest of our work in this course. So in our standard normal distribution, we're talking about a bell curve that has a normal probability distribution with a mean of 0 and a standard deviation of 1. The total area under the density curve is equal to 1. When we're looking for methods of finding normal distribution areas, i.e. our probabilities, whenever we look up the numbers, we have two ways of doing this. We can look up our numbers on a table. Appendix A2, I believe, has this one, and we can use Excel, and I will show you both. Whenever we get the area from Excel or the table, what it always gives us is the cumulative area to the left of a vertical line above a specific value z. Right? When we get areas that are bounded to the left and the right, we're able to use this fact and use the facts that we get from our table in order to find specific values. So one of the things that we're going to have to develop a skill to do is how do we find the probability under a normal curve for a continuous random variable that has some lower and upper boundary. Well, some facts that are helpful for using the standard normal table and for Excel. First of all, it's designed only for the standard normal distribution, which has a mean of 0 and a standard deviation of 1. It's on 2 pages, with one page for negative z-scores and another page for positive z-scores. And each value in the body of the table gives a cumulative area from the left up to the vertical boundary above that specific z-score. If we're working with a graph, we want to avoid confusion between two items. One is the z-score. A z-score is a distance along a horizontal scale of the standard normal distribution, and it refers to the leftmost column and the top row of the table. The area is the region under the curve, and we refer to the values within the body of the table to find these numbers. And the part of the z-score denoting hundreds is found along the top. Well, let's take a look at one of these here. This is a z-score table. If we're interested in finding it, our z-score is listed along the very first column right here and along the very top row, the hundredth position. Right? So we have two tables right here. One shows us to the left and one shows us to the right. Just a couple of notes about the little diagrams up on top to help you figure this out. If we're giving a negative z-score is one in which we're looking for the value of the z-score, and if the z-score is to the left of the mean, if our z-score is to the left of 0, we're going to get a negative z value, and you can see that's where this is. On the other hand, if our z-score is positive, right, here's our mean, it's supposed to be the letter mu, our z-score is to the right of that. So we know that if we're to the left or the right, a positive z-score will indicate we're to the right, a negative z-score will indicate to the left, and this is the appropriate table to use. Well, let's go through an example. Let's try this out. Let's say that I told you that I was interested in the probability that I had a z value less than negative 1.47. Well, what I would do on my tables, I would find, first of all, negative 1.4, which is the first two digits of my z-score. Then I'd find the hundredth digit. So the way we think about this negative 1.47 is it's negative 1.4 and 0.007. The hundredth place is always along this top row right here. And the ones and the tens place is right here along the first column. So we go to negative 1.4 and we look along that row and we look for 0.7. And here's the probability that we're given. 0.0708. So I would say this is my probability, 0.0708, or 7.08%. Right? We might think about it this way. Now, the nice thing about Excel is that it also gives us the values for the table. And in Excel, we're going to use a formula that looks like this. It goes norm.s.dist z in 1. Right? So if we wanted to give a z value right here, here's the way that I would plug in this formula. I'd substitute in negative 1.47 for my z-score, comma 1. By the way, the comma at the end of this is telling Excel, the program Excel, that we want the cumulative distribution function. So we're looking for our CDF whenever we put 1 in that place. The 1 is read by Excel as true. As in, do we want the cumulative distribution function? Answer true means that yes, we do. If we put a 0 there, or if we put false, it would be giving us the probability distribution function. That is our probability mass function, and that's that formula that we showed all the way up at the front of this presentation. But in any case, you can see that by using this formula, we get exactly the same numbers. So Excel is really just a way of getting that probability distribution, that value from the body of our table, pretty automatically, which is a nice thing. All right, well, let's try it out. Let's use the standard normal distribution, and this is an example. It says a bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. That's a disease that causes bones to become more brittle and fragile and likely to break. It typically happens over old age. The result of the bone density test is commonly measured as a z-score. So a population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1 so that these tests meet the requirement of the standard normal distribution. So what we're going to do is we're going to use Excel and the normal distribution function to illustrate this point right here. And we can also use the table, but let's use our formula right here. We're going to round our answer to 4 decimal places. So here's my first question. Let's say that a randomly selected adult undergoes a bone density test. We want to find the probability that the result is reading is less than 1.27. So what probability do you find for z being less than 1.27? Well, let's go to Excel and do this. I'm going to open up my Excel here. Let's see. Our probability that z is less than 1.27, the way we're going to find that is to just simply type it in. So we're going to equals norm.s.dist. Right? We can double click on the formula right here. As for a z-score, so we put in 1.27. And of course, as for true or false, we're going to put 1 for true. Close that. And there's our probability right there, 0.89796. So if I round that, so I'm looking for 4 decimal places, I'm going to get 0.89. Let's go back to my Excel table right here. 8979. Well, that's going to be 80 here when we round it. So we're going to put 8 and then 0 here. And this is my probability. So I've got an 89% chance, 0.8980 probability of finding an adult that has a bone density less than 1.27. Well, let's try it again. This time, let's say we're interested in finding the probability randomly selected adult, has a bone density greater than negative 1.0. That is 1 less than the normal standard deviation. Well, again, the relation we need to use right here is to recognize that if we want a probability that something's greater, we're going to use the fact that since the probability that z is less than, we could say that if we took the probability over here, this area in white, and added this probability area here in red, we should get a total of 1, right? So let's just call this area A and call this area B, right? Area A plus area B must equal 1. So if we want area B, well, algebra tells us that we're going to take 1 minus area A. And area A is the one that we get directly from Excel. So that's pretty helpful. So let's go to use Excel and try that out. All right, so our probability that z is going to be less than 1, greater than or equal to -1 is going to be the probability 1 minus the probability that z is less than -1.0. So that's how we're going to type in our formula. Equals 1 minus, and now we can type in our formula, norm dot s dot dist. You can pick it right off of the formula sheet right here. We're going to put in our z value of -1, and of course we're going to choose true and enter. Well, there it is. There's our probability, 0.8413. So that's how we're going to enter our value right here, 0. 0.8413. And that would be the area right here in red, 8413. If we were interested in finding the area right here in white, we could just subtract that from 1, and we would be back to where we started from the Excel formula. All right, one more. Again, using the bone density test, let's find the probability that the randomly selected adult has a bone density test value of somewhere between -1.5 and +0.5. All right, so in this case now we're going to have to do a little bit more juggling. There's 3 areas here. We're interested in area C, let's call it. So here's area A and here's area B. A good way of thinking about this is that area A, that's our probability that z is less than 0.5. Right? Now, we're not really interested in area B right here. We are interested in C. Well, we could say that areas A plus C would be the same thing as the probability that z is less than 0.5 right here. I think I just made a mistake, didn't I? Yes, I did. Oh, good job, Professor Peoples. Okay, so let's catch this one, right? At this bottom end, we wanted -1.5, didn't we? Right, so, okay, z is less than -1.5 right here. I need to take my time when I'm writing. All right, so what this little rule right here is stating is that, well, if we wanted the probability then between -1.5 and +0.5, we're going to subtract. Take the probability of the higher value, so the probability that z is less than 0.5, and subtract away the probability that z is less than -1.5. Right? So we're going to subtract those two, and that's going to give us our probability that c, right? Remember, we could think about it this way algebraically. If we took area A plus c, and we subtracted away area A, we're just going to be left with area C, right? Makes some sense, at least a little bit. So let's go to Excel and check that out. Here we go. So what we're going to do right here is we're going to take our 2 probabilities and just simply subtract. So we're going to take the norm dot s dot dist. In the first case, right, we wanted 0.5. That's the higher probability. Of course, we want 1 for true. And we're going to subtract away from that norm.s, again, dist, the standard normal distribution. And our z-score this time is -1.50. And again, we choose 1 for true. And there it is. There's our probability, 0.62466. Well, rounding that to the nearest 100th means that we're going to have a probability of 0.62. See, I can't remember digits while I'm talking and writing at the same time. 47, right? 47. Here we go. And that's what we wanted, right? So this is our probability right here. And so don't forget, our notation right here is that if we say the probability that z is somewhere between 2 numbers, a and b, well, that denotes the probability that z is between a and b right here. And we do that by subtracting, right, our 2 probabilities. Probability of the one on the right, probability that z is less than b, pardon me, I'll write it this way, z is less than b. Wow, boy, I'm having trouble with my leaky marker today, guys, sorry about that. Probability that z is less than b, and we subtract from that the probability that z is less than a. If we want to get the probability that z is greater than a, don't forget that's where we're going to take 1 minus the probability that z is less than a. And if we want to get the probability that z is less than a, that's the one we're either going to get from the table or Excel. All right, so for right now, that's what I have. We'll have more in the next video.